Um, I'm going to keep an eye on time here for you guys. So, my name is David Long. I'm at Flathead Valley Community College, and I teach chemistry. I used to teach down there at MSU and do research, the same department that David Sands is in. And I always love doing this lecture, but I got to say, I'm not too excited about this scenario, and meaning being up here in Kalispell, and you guys scattered around the countryside down there in Gallatin County. But the reason is my thing is to teach and communicate with people. That's what I feel is the most important thing I can do now as far as bolstering the role that science plays in our society and in our lives. And it's really tough to do. I can't see a single face. Um, and teaching and learning is above all an interpersonal thing, and as you know, something like 90% of our ability to communicate is nonverbal. So this kind of sucks for me, but I know it sucks for you too. But I'm really happy that we can at least do this. So I'm going to take about 35 minutes to talk about some student research projects that we do here at Flathead Valley Community College, and we have a bit of a different philosophy behind how we incorporate students in research. And so I'll talk a little bit about that, but I'll mostly vent. And what I'm going to vent about is how you, me, all of us need to become involved in science in one way or another. And I'm going to talk a little bit about why we do this as scientists. And so I think you've heard some very, very important talks about, COVID-19 and virology and some things that we would all agree, like, wait a minute, this is super urgent. I'm going to talk to you about some planetary science that might not feel as urgent, but my main message would be that you've got to get out there and do what you love and make science a part of what you love. I mean, I'm not admonishing you to do that, but I'm trying to communicate to you some of the real joys that we experience as scientists. So let me tell you about a place we go to. This is a Google Earth image, and the planet is rotated in an orientation that you would never have bothered with, but that I bother with all the time. And so this is the west coast of the U.S. You can see the Baja Peninsula up here, and down here we have New Zealand and the coast of Australia here. Right there at the end of that arrow is a place that we take students from our college and from MSU. We've taken several MSU students, one U of M student, and we take people there to study ocean water chemistry. And when you look at the way the planet is oriented here, it becomes apparent, like, wait a minute, that island, Moorea, it's not at all far from Tahiti. That island is in the middle of nowhere, but in the middle of the ocean. So we study the role of carbon dioxide and how it affects ocean water chemistry. So carbon cycles through the environment, through ecosystems. It doesn't pass through the way energy does, but it cycles in ecosystems. And the hydrosphere is all the water on the planet. There's a lot of that, as you know. The atmosphere, you know what that is. Those are the gas phase materials that blanket our planet. And then there's the lithosphere, the salt, you could say the solid parts of the planet. And all these are interconnected. Carbon appears in all these realms in different forms. And what we study is the circulation of carbon in these different forms on the planet. And we go to this island. This is Moorea. We actually go to two different islands, and there are labs there. And these labs are in the middle of that Pacific Ocean, given that picture I showed you representing the planet. So this island, Moorea, is a high volcanic island. This picture I took with a telephoto lens from Tahiti, so that shows you it's only an hour or so boat ride between Tahiti and Moorea. And on that island are some very remarkable things. This is one of our students, Tia Luciano, taking a break from doing her chemistry and enjoying the environment. And she has a relationship with this organism that you see here. This is a black-tipped reef shark. And she's sort of interacting with the thing, and she's experiencing it through a medium, and the medium is this seawater that's even difficult to see. It's incredibly transparent water because it's low in nutrients, it's low in particulate matter, and you can see 100 feet through some of this in some areas on this island. And we're very interested in what's dissolved in this water and what this medium is and what changes the chemistry of that medium. So let's go to a figure that I think a lot of you have probably seen. This is carbon dioxide plotted on the y-axis, and on the x-axis we have year. And this is data that's recorded from Mauna Loa, famous the so-called Keeling series. And this is carbon dioxide levels as a function of time since about 1960 to say 2015 or so. We're recording these values for a very important reason. They're rising. So as the human race burns fossil fuels, we're putting CO2 into the atmosphere. And these are the measurements that show that. And it's steadily going up. And so you've heard about global warming, and you know that the big discussions going on about what are the implications of rising CO2 in the environment. Well, one of them is that the carbon dioxide dissolves into ocean water. So this darker blue data is a trace of measurements made of CO2 dissolving in seawater. So carbon dioxide is a very interesting stuff. I'm going to flip to writing a little chemistry here, and I'll show you a slide that represents this. But carbon dioxide is this molecule, and when it dissolves in water, it actually reacts with the water. So normally when I talk to an audience like this, I'll ask, raise your hand if you've had some chemistry. So I have no idea who has and who has not had any chemistry. Doesn't much matter. We can explain what happens. This molecule is the carbon dioxide. It reacts with water to form this completely novel stuff, this carbonic acid. And this carbonic acid, this stuff is a source of these things, which are protons. This is the business end of an acid. And so as the carbon dioxide dissolves in seawater, it affects pH of the seawater. So that's shown here, where the pH of the sea, the open ocean, we'll say, has dropped about 0.1 units since the advent of the Industrial Revolution. So 0.1 units is about a 30% increase in proton concentration or hydrogen ion concentration in the ocean. It's an acidification of the ocean that, were it to happen to your blood pH is about 7.4. If this kind of shift occurs in your blood pH, you're usually ending up going to the hospital because something's pretty wrong. So it's, in effect, a chemical heartbeat of the ocean. It's like the super fundamental variable that all sorts of myriad of chemical processes tie into this hydrogen ion concentration. And because of that, it's like a central variable that everybody's interested in. All chemical oceanographers, you won't find one on the planet or off the planet or in another solar system or whatever who isn't very focused on this as a central variable. So that's what we're interested in. And what we do with students is take them to these places and have them make their own measurements, verify for themselves whether this is happening or not, and then develop their own ideas about how to proceed or what we might do about it or whether we want to further explore it. It's their deal, their experiments, their projects that we help them develop. So before we get back to the chemistry, there's some physics too, some planetary physics, I guess you could say. Water stores a tremendous amount for every degree rise that it heats up. So the oceans on the planet, though the global temperatures may not have increased much, enough to concern an awful lot of people. The oceans are storing enormous quantities of energy. And so when you read studies of, wait a minute, what are these hurricanes doing? Like, these hurricanes essentially harvest energy from the atmosphere and the oceans. And when surface water temperatures are higher, a much greater amount of energy is available to those storms. So this is a separate climate-related problem that CO2 is causing. CO2 in the atmosphere blankets the planet, creating the so-called greenhouse effect. This pH business and the acidification of the ocean is a second and somewhat separate consequence of this CO2 rising on the planet. Make no mistake about it, for those of you who have not studied climate science or haven't had the opportunity to study chemistry and biology and think about how the planet functions, these are measurements that the human race is making. These are not speculations. These are not conjectures. These are measurements that we're making. So we've had 10 to the 17th grams of CO2 dissolve in the oceans since the Industrial Revolution began. And the kicker is, here is the change in seawater, surface seawater pH. You could say as a function of your position on the planet. And you can see the red represents a larger pH change, the blue and green lower pH changes. Some of this is modeled because we can't make these measurements around the planet. And one of our goals in our program is to develop instrumentation so that people like you can grab a little instrument that you run with your cell phone. And if you happen to be up doing something in Greenland because you like to go to Greenland, you can take some pH measurements and upload them to a database that will map the pH of the oceans globally, across the whole globe. We're not that into fancy schmancy science instruments that cost hundreds of thousands of dollars, for the simple reason that we can only make a few of those. We can only deploy a few of those. But we want to make cheap, good instruments, throw them across the planet, have every culture have access to those, and be able to better map and understand what's going on the planet. But the pH change is not even around the planet. And before we get into our program, I want to segue into what you might be more familiar with in your chemistry class. Here's a guy doing what we call a titration. And it's essentially watching clear liquids drip under fluorescent lights with cinder block walls. That's not the way to turn you on to science. We titrate sometimes hundreds of times a day in the field on these islands that we go to. It's an extremely important technique. It's universally applicable to all kinds of great chemistry and even biology. But it really sucks to have to do this before you know why you would even want to do it. So we have education in the sciences backwards, and a bunch of you think like, this is not for me. I'm a creative type. I don't like watching clear liquids drip. Neither do we. In fact, we probably dislike it more than you do because we've done it for so many years. But what we really love is the results that we get from it, the progress that we can make. And it's an extremely exciting thing to design your own experiments, your own research program, go out and discover real things. So I'm going to tell you about some of the things that my students have recently been working on. Let's do a little bit of chemistry. This is a periodic table. This is a rendition of the periodic table. These are all the elements, all the chemical building blocks that are available to us on this planet. And the height of the columns in this figure are proportional to the abundance of that element in seawater. So the first thing you should notice is like, wait a minute, there's a heck of a lot of stuff in seawater. It's not just salty water. It's not just sodium chloride. It's got almost, you could say, I'm sure, it's got all soluble materials. The planet is dissolved in the sea, is one way of thinking about it. So these are the Legos upon which all chemistry and biology are built. So if you look at the height of the column, it's proportional to the abundance of the element in seawater. The colored columns are elements that are used by biology. So it's probably no coincidence that biology takes advantage of all the chemical building blocks that are available to it. So this is kind of a topo map, or a three-dimensional contour, a chemical landscape upon which the biology grows. And so it's the ratio and the absolute amounts of each of these elements that matters a whole lot when it comes to biology developing in a seawater chemical background. So if you tweak any of these column heights, it tends to really ruin some of the biologically relevant chemistry. So some of you has balanced equations in chemistry class, and so you know the atoms in or the atoms out. If you start with 10 carbon atoms, you're going to finish with 10 carbon atoms. And up here in the Flathead Valley at the Flathead Lake Biological Station, the director of that station is a gentleman by the name of Jim Elser. And Jim is a National Academy of Sciences member. He's a fantastic scientist. He wrote this book, Ecological Stoichiometry. And this is the idea that if you balance one chemical reaction, and you've got two, well, the two have to be balanced, and you have four, and so on and so forth, until you can build all the way up to ecosystems and treat them like simple chemical reactions. If you put too much carbon in the water, you're going to screw up the stoichiometry, or the ratio of the elements in the ecosystem. So we go there. We go to this place. This is Moorea. And right here, there's a lab that's run by UC Berkeley. It's a chemical oceanography lab, primarily chemical, but also biological. And there are dorms and huts there that we're able to stay in and design our own experiments to study primarily the development of this thing that you see here. This is the reef around the island. It's a coral reef. It's a living thing. It's an assemblage of organisms that accrete stone. So this rim of stone is calcium carbonate that is a biologically mediated deposition of a geological feature. So you know that thing about, hey, you can even see the Great Barrier Reef from space, Google Earth. Sure you can. You can see these reefs too. And you can see they protect this volcanic island. There are people who live here, like people who have lived here for thousands of years, cultures who have developed over thousands of years that are potentially at risk if all these organisms die. If the organisms growing the reef die, there's going to be some very bad consequences in places like Moorea. So we go there and we stay at the lab and we execute our own experiments. We interact with the scientists there, our students, alongside some really fantastic science folks. And again, we go there because it's in the middle of the ocean, and we go there for other reasons too that I'll show you. Here's a schematic of the island, and in each of these locations, these yellow boxes you see, there's a bunch of little dots in there. These are instruments that the National Science Foundation has deployed long-term. So this island is a long-term ecological research site, and they're taking the stance like, look, that CO2 trace that's going up steadily, the reason we know it's going up is because Keeling refused to give up through all the way since the 50s, making those measurements. Long-term monitoring of the planet is really, really important. So they've set up these instruments, some of which measure pH, CO2 concentrations, phosphate concentrations, temperature, all sorts of variables, because we want to watch so we have the ability to know what's going on in the planet. So we have access to all the data from these instruments, and we're treated just like any other scientists when we show up there. In fact, we're treated a little bit differently. We're the only people from Montana who go to the two islands that we go to. And it's not a bad place to do science. This is a legit, straight up lab facility right here. And it looks like a little hut by the water because it turns out it's a little hut by the water. And all you need is some power and some picnic tables and all your stuff with you. Behind this are some advanced labs with all the sort of equipment that you might see in the States, but there's also opportunity to be outside and experience the environment. So this is about 2.5 million-year-old islands, something like that. These are volcanic islands, and they're absolutely fantastic places to be. And one of the reasons we go there is to be there. And what I mean by that is when you get out and you make an emotional connection to what you're studying, now you're doing science the way scientists do it. David Sands doesn't care about certain things. He cares about other things, and he cares about those things a lot. He's passionate about what he does. And I'm pretty sure if you search your memory and say, wait a minute, which of the speakers in this class were passionate about what they do? They may not be all outward, hand wavers like I tend to do or whatever, but make no mistake about it, they've made an emotional connection to what they do. It's exciting and interesting, and they're compelled to do it. That's what you got to develop as a beginning scientist. And I'm super concerned that we aren't able to talk to one another face to face. You're in your formative years of developing as a scientist, or at least a citizen interested in science. And it's tough right now. We like hanging out. We like shooting the bull with each other. We like talking about what we do because it's important to us. And we need people interested in everything: human health, agriculture, you name it, there's a place for you. So we, in my lab, we're all interested in what you can't really see here, this water. So most of you see biology. There are organisms. These are corals growing, and the coral is more or less an assemblage of a photosynthetic organism and an animal working together. But there's a very, very thin film of living tissue over the top of stone. So really, another view of this, most people see the coral, but we see, well, wait a minute, there are all these elements that I showed earlier in the seawater, in this water, and then there's the stone, the calcium carbonate, and the biology just mediates, and you could say moderates, the accretion of the calcium carbonate, the stone. Without the stone, you got no island. Without the island, you got no people. Without people, you don't have the same planet, so on and so forth. This is important stuff to understand how this all works. So here's an example. This is a bleached coral colony, and you can see these brown colonies in the background. I'm going to take a look at time here. We're good. These are seemingly healthy coral colonies. This one is not. It's not dead though. One of my students took this picture on Maria while they were doing their work, and they decided, something's way wrong here. You told me I wouldn't see any bleached corals when we came here, and they're all over the place. And so I said, well, yeah, I was told that there wasn't any bleaching. This is, I believe, 2016 we were there. And so there is. So this student got very interested in this on the ground, on the spot, designed some experiments to quantitate this because they felt it was very important. The coral has kicked out its what the photosynthetic partner that it has. They're called zooxanthellae. And it's not dead yet, but it will probably die unless it picks up more of these things from the environment and then turns brown again. And so what these students did is they said, well, look, wait a minute, this has got to be very important. We know about coral bleaching. It's in the news all the time. We want to quantitate it. We don't see anybody else around here doing this right now. So we want to design some experiments. Here they are at work. Now, this is more like what a lot of chemists do. David Sands, before COVID-19 rolled on to the scene, he was flying all over the planet, all over the place, in all these sketchy, iffy countries that he loves to go to because there are people who might benefit from what he's interested in, and politically unstable place, all these places he goes to. And so his work is not sitting in the lab under fluorescent lights, and neither is ours. In fact, it's relatively rare these days, I think, to be locked up in one lab for your entire scientific life. You got to be a bit of a generalist, and you certainly, to enjoy what you do, have to be willing to do things like jump into water where there might be sharks and just get your work done. This is super fun, by the way. The environment is unbelievably stimulating. And I thought about taking students to Iceland to study volcanoes there that are spewing out sulfuric acid and just killing everything downwind of them. And I thought, well, Iceland in January in the dark with concentrated battery acid all over the ground is probably not as fun as going to these places. So we decided let's go to Tahiti instead. And by the way, if you make a hard, good pitch to a good college, they'll listen to you. They'll listen to crazy ideas like, we should go to Tahiti and do chemistry. They don't listen at first, but if you're persistent, remember, if you got an idea that you feel is good, go to start with SANS. Start with some of the other faculty members who are go to the look. Listen, I got an idea, and you will be heard. I guarantee you will be heard. So here's Audrey Jones, one of my students. She's an absolute beast in the water. She's a competitive swimmer, was highly ranked in the state of California in high school. So we made her take the cinder blocks, and these are instruments that we deployed in the water. And so everybody has their role. So make sure you've got an Audrey along. And what we did is locate monitoring devices. In this particular, this is two students' projects. Locate these monitoring devices around the reef to monitor not only temperature, but light levels, pH levels, some other things. So just the work of deploying the instruments takes a couple days of really hard physical labor in a very beautiful place. It feels more like hiking at that point because you've done your hard work of trying to figure out what to do, and now it's a matter of executing. And then you get data sets like this. So this is a particular week in a bunch of years here, all the way from 2006 up to 2016. We measured temperature during that week of the year on the reef, where the National Science Foundation, as I said, they have a long-term ecological research site, and they've monitored temperature for many years there. And we showed that that particular week that we were there, indeed, the water temperature, this is our data, this is the National Science Foundation's data, and the students designed, built, executed experiments that monitored reef water temperatures and showed that no, that indeed the reef waters are elevated in temperature, which is a variable that correlates with that bleaching, which is what they were interested in. So they then quantitated bleaching by photographing reefs, counting colonies that are bleached and unbleached, and came away. This is the stuff you see in a journal article. You don't see the stuff where leading up to this. This is a really exciting data set to us. Basically, just to summarize, it shows us what % of colonies of different types of corals are bleached. We were the only group to make those types of measurements that year. The only data available for Moorea were collected by community college students who a lot of scientists would say, what do they know? You know, they only had 1 or 2 chemistry classes. Well, some people have called us about, hey, can we take a peek at that data? It's pretty interesting. This activity, this business of doing science, I'm showing you this to emphasize it's not what you think it is. So it really stinks when you get the impression from your chemistry class that doesn't even put you in contact with the science. It's only the techniques. You can learn the techniques later. You have to get excited about the science, involved in it, and then you'll be motivated like, wait a minute, I got to go learn how to titrate. So I'm going to finish up here with, we've got about 7 minutes, I guess. I'm going to finish up with a separate project. So I mentioned, we're very interested in seawater pH and the effect carbon dioxide levels have on that. And that ties into the bleaching because both decreases in ocean water pH and elevated temperatures are known correlates to bleaching. This guy, I'm going to tell a little story about this particular student. This guy, he graduated from MSU. He was awarded, I'm not going to remember the name of the award that he received, but the most celebrated electrical engineering student at MSU. He started here. I won't tell you about his life prior to entering college. It was a bit rough. But once he found science, things changed a lot for him. And he built an instrument that, I'll skip down here. This is 3 of his small instruments. They're small, they're light, they're portable. They measure pH with extreme precision and accuracy. Like, these are really good little things. They're cheap, they're easy to build. He figured it all out. He runs them by an app that he wrote for his phone. And in this picture, he's comparing the performance of his cheap, inexpensive, easy to build instruments with a super fancy instrument that's interfaced with this computer made by a company in Missoula, Montana. And I told him, like, hey, William, we need an instrument that just isn't available now. Could you possibly build us one? And he did, and it's in commercial production now. And so there's a story behind how it all happened. Here he's running, testing instruments side by side, doing his science. This is on Moorea in a dining hall. There's a bunch of coffee cups here. Real life and science life get all mixed up, and that's when it gets fun. What we did is take these instruments as a group of students out onto the reefs, and we measured pH all over the place. And our idea was to map ocean water pHs, like I said earlier in this class. And we came back with some data sets that really blew this company's mind, the company that makes this expensive instrument. So I'm going to show you just one of those data sets. We also go, in addition to Moorea, we spent about a week or week and a half on Moorea, and then a week or week and a half on an atoll called Tetiaroa. And this atoll was owned by Marlon Brando. And before he died, he left it to science, essentially. He said, look, you can have a little bitty eco resort on one of these 7 islands, but I want a lab there, and I want nobody on all these other islands. And I want to protect them as a place where people can go to do the types of science that we do, study ocean water chemistry. So we have access to a lab on this island that is extremely difficult to get access to. But the people who run the lab, we made relationships with them, and they get what we're trying to do. And so the experience of being here is indescribable. I don't have time to talk about it, but if anyone's interested, they can email me. I'll give you my email at the end of this. But what we did, here's a sample data set. This solid black line is pH fluctuations in that lagoon, the interior between those islands that I just showed you. The little blue dots that you can hopefully see is Williams' instrument running alongside the expensive instrument. And you can see these fluctuations in pH as a function of time of day. And so all of a sudden it's like, wait a minute, if pH is being dropped by CO2 dissolving in the water, wait a minute, that's not it. We got a much more complicated situation than that. It's fluctuating up and down with the day-night cycle in this lagoon. So there's a lot to be learned, is the point. A whole lot to be done, a whole lot of cool things out there to discover. The deal is that his instrument worked so well that he came back from Moorea with a data set, multiple data sets, that we went down to this company in Missoula who makes the world's best pH measuring devices. You might be surprised to learn that in Montana we have chemical oceanographers, and the world's best instruments by a bunch of different measures are made in Missoula. a company that was spun off of a University of Montana chemical oceanographer there. So even if you don't want to leave Montana, you can study ocean water chemistry. We proved it. They proved it. Sure, you could. Yeah, absolutely. But this guy, William Pardis, he came back and he showed them his data set, and they hired him on the spot. They they became our partners in the development of his instrument. Subsequent to that, he easily got into Woods Hole's summer program. Woods Hole is a marine lab on the East Coast that's associated with MIT and Boston College and a bunch of other places. It's harder to get into their summer program than it is to get into MIT's graduate program in engineering. So he got into that summer program. Then he worked as a professional engineer for them while he was going to school at MSU before he finished his degree. And then Woods Hole / MIT hired him as a full-time engineer, and he's working in that lab. It all started, he deserves absolutely 100% credit for this, but it started with him saying, wait a minute, there's an opportunity for me here. I can make a difference. The guy is just ramping up like nobody's business, doing what he loves to do. And we've had many, many examples of students being able to do this type of thing. As faculty, if we just give students a chance to come into the lab, be full-fledged members of the group, bring their ideas, bring opportunity to them. And this happens every day at MSU. It happens every day at universities and colleges around the world. And it's incumbent upon you to take the bait. If you see yourself becoming a scientist, get out of the classroom, get involved with what some of us might call real science. Classroom is like lifting weights in the lab, or excuse me, in the gym. The science is like being on the field playing the game. Why would you just lift weights your whole career, not ever having your academic career, not ever having played the game, and then decide you want to go play the game? So get involved. And if you're not doing science, if you're in other fields, we need you to be involved too. So I'm going to finish up here, but usually, well, sometimes I guess David has said, if you had $3 million, what would you do with it right now? Well, what I would do with it is what I'm doing now, but I would do a lot more of it. And that is doing what I can to communicate science to people and get people involved. We are at, make no mistake about it, we are at a crisis point when it comes to how our society is incorporating scientific ideas into their activities and into their consciousness. We're screwed right now. We got to do something about it. And no, I personally wouldn't go study COVID because that's not my jam. I would say we need people to communicate science to people like this class does. So I'm a big believer in the structure of this class and the way it works. So I will stop there. I don't know how you guys do questions or how you want me to proceed from here. Silence on this end.
Oh, they won't be silent for long. There'll be a question here.
Okay.
I see one back there. Hang on, I'm walking to it.
Are there any other kinds of experiments or labs being done in these islands besides the ones that you're doing?
Well, not only are there other, I would say the majority of what's being done is being done by other scientists in other labs. So both these labs have a regular sort of population of science students, mainly graduate students, and scientists that show up doing a wide variety of things. So yeah, there's lots and lots of science going on at these two labs we go to.
Here's another one.
So how did you get started in science?
Actually, um, I'll give a quick anecdote that I think is related. When I was a kid, I grew up in Green River, Wyoming, in the desert, and the famous Green River sandstone formations have fossils in them, and so there are these fossils up and down these desert mountains. And I spent summers in Cape Cod, by the ocean side with my grandparents, where there were live fish, and I had this problem. Wait a minute. Um, what? How is it that there are fish in the sides of these desert mountains that are dead, and then we've got these fish down in? I don't understand the situation. And most people, my parents, would say, "Oh, uh, those are fossils." Like, okay, great. I know they were called fossils, but I don't understand the system here. And they would, "Oh, go wash up your hands, go, we're gonna have dinner." And no one ever sufficiently explained it to me. And I had a lot of questions like that that had no answers. And I count that as a major reason I became a scientist, that uh, people just didn't feed me answers. They gave me an opportunity to think about how the hell to find answers myself. That's the exciting part. So I think I had an opportunity in that way that wasn't intentional in any way. It just happened to me. Um, and I do count uh, being outside and experiencing the planet as a pretty large influence as well.
I've run into a recent problem that maybe we could collaborate on. There's a lake in Montana that has 5-inch thick diatoms floating on top, and it's only one lake, and we haven't seen any others like it. Do you care to work with me on that?
I do. Um, that
That's all you need to say. I'll contact you later.
Yeah, but it brings up a point that, well, 2 points. Number one is we are adapting our instruments to freshwater chemistry analyses. It's tough, for various chemical reasons to do, for example, CO2 concentrations in fresh water. But um, if you're wondering, wow, can we go backpacking and measure pH of these high mountain lakes with these instruments? The answer is yes. Is it important? Absolutely, it's important. And the other thing is, um, the idea that you live in Montana and you study the ocean isn't crazy. With 70% of the planet ocean, don't, as an inland student or scientist, you might be interested in your immediate environment. I hope you are. But, David's saying, well, would your students be interested in going to this lake and making some measurements and seeing, oh, hell yeah. Yeah. The planet is a place, one big place.
Well, you could also come to Kenya with me, where we give them 3 months extra food. There's a bunch of things that students can do. And one thing is you do get to travel. That's kind of neat. Not this year, maybe, but often you do. Uh, Tell them about your education. Said in fishes, but tell us your life history a little bit.
So I've been in, I uh, I hesitate a little bit because I am so lucky. Um, I am so fortunate to have had educational opportunities that many people haven't had, and people from Green River, Wyoming, who I knew didn't have. And it's another reason I take this business about, wait a minute, we gotta pull people up. We gotta spend some time doing this. I went to Penn State as a chemistry student. Did very well there. Got into Caltech as a graduate student. Um, did very well there. Did a postdoc at the University of Colorado with a Nobel laureate. Did great there. Went to MSU. Had a research career there. Was fantastic. Moved up here. Do teaching now mainly, though I do this student research. But related is, this week, 2 people I know received Nobel Prizes. one, Jennifer Doudna for molecular biology, that the CRISPR techniques I'm sure you guys have heard of in this class. And a second, my old graduate school roommate who is now his wife, and she received a Nobel Prize for her black hole work. So, I mean, I have been around some folks who have made huge impacts. And I just did a class yesterday where I told the students, if you knew these people, I'm not name dropping. I'm trying to make the point that they are just like you guys. They're just people who were very excited, very talented, no question about it, very focused, no question about it, but they love what they do, and they end up making these huge impacts on the future of the planet and the human race. And of course, it's people just like you. You have great advantages. Those, I could say a few things about the students at MSU because I know you. I used to teach there and work there, and you have great advantages over some folks. You have a less structured environment. You're more prone to be creative about making a situation that is fulfilling to you and that you like. So those of us who come from these rural environments, I think there are some advantages to that. There are a lot of disadvantages, but I would say I'm a Western person, like most of the folks in this class probably are. Came from a small town, and I was damn lucky, very lucky.
Okay, I'll show you how we do this. All you guys, whether you're taking this course live or taking it online or watching online or whatever, you've been given $3 million. Okay, I wouldn't try to cash the check, but the fact of the matter is, given $3 million, what would you do to further biotechnology, further science, further yourself, whatever? And by the 16th of October, you at least need to write a brief description of your plan. It's in D2L, so if you go to D2L, you'll figure out how to submit this to Duncan. And Ed Dratz and I and several others will look these over. We will not grade them, but we will comment a little bit on them and get them back to you, because the final exam at the end of the semester, we expect you to turn in a complete plan, like 2 pages. So you can see that by the 16th of October, please submit something to show that you're listening and you're trying to figure out what to do with the $3 million. Thank you. Dave, if you have any more comments.
Just one, maybe. I think that under the current environment we're all operating under, it can tend to beat a person up a little bit. And I think that optimism, it's very difficult to do science if you don't have some degree of optimism. Say, wait a minute, this really difficult thing that no one's ever been able to do or figure out, I'm going to take a crack at it. Protect your own optimism in this environment and say, wait a minute, this is going to pass. We're going to, the opportunities are always going to be there. The exciting things are there to be done. In the meantime, we can operate in a way that will push us forward while this is going on. But a lot of my students are discouraged right now. It's tough, and so I would say, protect that optimism, that positive outlook that's there, because it's really important when you go to be a scientist.
Protect your optimism. Good luck on the midterm. submission of a good idea, and we'll comment on it. Thank you. Bye-bye.
Thank you.